Not too bad, right? And some people figured it out and just went to the YouTube. So we are happy today to have Mikael Backlund of our own Department of Chemistry here at Illinois. Mikael did his PhD at Stanford and then a postdoc at Harvard before coming here and joining our faculty last fall. And it is March 2nd, 2021.
Whoops. I swear I didn't give this exact talk a year ago.
As usual, feel free to put your questions in the chat, or if there's something urgent, you can raise your hand or maybe even just interrupt Mikael if that's okay with him.
Sure.
And I believe there's no seminar next week for March meeting. So go ahead, take it away.
Great, thanks, Elizabeth. Yeah, so I figured this talk would be as much an introduction to those of you in IQUIST I haven't met yet, which is to say most of you, as anything else, but I will, of course, talk about science too. But just a little bit about myself and my group. So as Elizabeth mentioned, I'm in the chemistry department. I started last fall, so yeah, August of last year. Our lab renovations are complete as of a few weeks ago. So we're moving equipment in, daily or so. But still waiting on some major pieces of equipment before we can really get started with our research. So right now we have 4 PhD students, 3 in chemistry, 1 in biophysics. So would love to have a student from physics or ECE or another department. So feel free to send them my way. And what our lab does in a nutshell is we develop microscopy tools that incorporate some elements of quantum information, quantum sensing, and apply them to problems in the molecular sciences. And so by molecular sciences, I mean things ranging from molecular biophysics to chemical physics to soft condensed matter and more. So as I mentioned, our lab renovations are now complete. And so I thought I'd map out what our lab looks like and where we are. So here looking at the map, over here is Loomis, and here's the rest of engineering. And here at the red star is where my lab is in CLSL, Chemical and Life Sciences Laboratory. And right now we have quite a bit of space for our 4 students. So this side, there's like a wet lab side and an optics side that's ready to be filled in with optics tables whenever they arrive. Things are a little delayed by COVID, but overall the schedule's gone pretty smoothly. And our research is most neatly divided into 2 categories, sort of the 2 sides of my lab. So on the one hand, we're interested, or we're developing a view of single molecule fluorescence microscopy as a quantum estimation problem, and seeing what new microscopes that leads us to design, and then what new capabilities in microscopy that enables. And on the other side of the lab, we're interested in doing nanoscale magnetic resonance microscopy using nitrogen-vacancy centers in diamond, which I'm sure many of you are familiar with. And okay, as I mentioned, my lab is still just getting started, really. So what I thought I'd do today is primarily talk about 2 projects from my postdoc years that set the table, I think, for these 2 thrusts in my lab. So that's work that was published in these papers in the past few years. So I'll start with a project that's related to this side of the lab, viewing single molecule fluorescence microscopy as a quantum estimation problem. And so a little bit of background here is that my PhD was in single molecule microscopy. So I worked for W. Murner at Stanford. But this was before there was any quantum flavor to my research, but there was some information theory flavor to my research even back then. And so I and many other quantitative microscopists got used to thinking of things like single molecule localization, localizing a single molecule localizing its position as a parameter estimation problem. And so what I mean, just to illustrate what I mean here, so at the object plane of your microscope, so now just in one dimension, the position of the molecule, the distribution that describes the position is of course a delta function centered at the true position of the point source. But then the problem is that once the signal actually gets to our detector, it's been corrupted by the point spread function. So meaning that the wave has had to pass through certain apertures in the microscope and it diffracts, as well as noise. Even if in the absence of electronic noise or additional background light sources, we always have the noise just associated with the Poisson statistics of the signal photons themselves. And so our task is to turn this noisy, corrupted measurement somehow into an estimation of the center position of this original delta function. So let's add a dimension now to make it more relevant to actual single molecule imaging. And okay, so now we're in 2 dimensions, and it's the same concept here, but it gets a name in our community called superlocalization. So the idea is that we might have the image of a single molecule that itself has an extent of a nanometer in linear units. It will appear on our camera as a blob that's hundreds of nanometers wide because of diffraction, and it will be noisy, as I mentioned. But we're not doomed to only make statements about its position with precision on the order of the diffraction limit, because we can look at this distribution and estimate its center position, the center of the distribution, which we assume to correspond to the position of the molecule, with precision that goes as 1 over the square root of the number of photons we record, right? This is just basically the central limit theorem. And so in this way, if I have a well-isolated molecule on my camera, I can localize its position with reasonable photon counts to single-digit nanometers or 10 nanometers precision. And so this superlocalization is one key ingredient in one type of super resolution fluorescence microscopy, wherein an extended object that's labeled with many, densely labeled with many fluorophores is the fluorophores that label it are made to blink in some way such that in any given image, you only have, a sparse distribution of single emitters that you can then super localize and then over time build up a kind of pointilless reconstruction of a super resolved image. And now from 1 dimension to 2 dimensions, now to 3 dimensions. 3-dimensional imaging is a topic I've been interested in since my PhD, and many other microscopists are interested in. And it's notoriously challenging, basically because that extra dimension, the depth, the Z position, is not given for free by the microscope. And so qualitatively, you can understand this as derivatives go to 0 as in the PSF as the object goes through focus. And so things change slowly. You have relatively little information near focus about the Z position. It also blurs, the PSF blurs quickly as you move away from focus. So you lose information outside of a very narrow window in Z as well. And so we can make these kind of qualitative statements about how a microscope doesn't give you very much information about depth by introducing concepts from even classical information theory, like I mentioned. And so revisiting our 1-dimensional illustrative problem of trying to localize a molecule given its image being corrupted by diffraction and noise, we can formalize our thinking of how precisely we can take this noisy measurement and turn it into an estimate of position by introducing concepts like the classical Fisher information and the classical Kramer-Rao bound, its inverse. So basically taking this probability distribution and computing how much information it carries about the parameter we want to measure. In this case, X, but X, Y, and Z more generally, or other parameters too. And I'll say that concepts like this from classical information theory, Fisher information and the Kramer-Rao bound, are quite ubiquitous in the single molecule microscopy literature and have been, say, over the past like 20 or so years. So this is something that I learned as a single molecule microscopist from the people around me. Okay, so now returning to 3 dimensions, we can compute the Kramer-Rao bound associated with just an off-the-shelf standard microscope. Kramer-Rao bound being the lower it is, the better we can estimate that particular parameter. And so a standard microscope, we can boil it down to just 2 lenses, basically. One, the objective lens that collects light from the molecule, or the rest of the many molecules in the object plane, and a tube lens that focuses that collected light onto a camera where you record an image. And for this standard microscope, the Kramer-Rao bound as a function of defocus, really just so we have some parameter against which to visualize these numbers, look like the following. So for lateral position, we have this dashed line where, okay, some obvious things we can pull out from this are the fact that in focus, basically this is saying you have your tightest precision in XY localization you can achieve, which makes sense, right? And here is the Z Kramer-Rao bound for the standard microscope as a function of defocus, where now you can see quantitative reflections of the qualitative statements I made a couple slides ago, like, well, near focus, the derivatives go to 0. And so basically you have the information about depth near focus goes to 0. And in turn, the Kramer-Rao bound blows up. And also as you move away from focus further out, you also lose information. Okay, so that this is relatively worse than X and Y is known, and that it blows up near focus is also known. And so to tackle this issue and perform 3-dimensional single molecule imaging, microscopists have now for decades been coming up with new ways to engineer their microscope to stick new, optical elements between the objective and the detector that somehow pull out more information about depth, about Z position. And this is just a quick survey of some of these many methods. So this could look like some sort of multifocal imaging or appending a 4F system to your microscope and putting some phase modulating device, spatial light modulator or something halfway between that 4F system so that you reshape the PSF in a way that gives you more information about Z. So this has been done for many years. And what else has been done is to use the Kramer-Rao bound, this concept from classical information theory, as both a metric to help the design of these engineered microscopes for 3-dimensional imaging, as well as a way to compare between the performance of different engineered microscopes. So what I'm showing you here is just one of many works that do exactly this. This is from my colleague, Yoav Sheckman, who actually was a co-author on the paper I'm going to tell you about, where he was developing these tetrapod, or actually these are called saddle point. He also developed something called the tetrapod. These saddle point PSF, so some shape that gives you relatively more information about depth, and you can compare its performance to other microscopes that have been invented for 3D imaging specifically, and assess whether you want like better precision over a narrower range or worse precision, but more over a flatter performance over a large Z range and so forth. But this naturally leads one to some more general questions, like how well can any designed microscope perform? And for this task of 3D imaging, or more generally for other estimation tasks, and do these established microscopes that people have invented now for decades to do 3D imaging actually attain that fundamental bound? If there is, if it makes sense to even talk about a fundamental bound. And so what I'm going to talk about today is projects in which I explored this idea that if you view this as a quantum estimation problem rather than just a classical parameter estimation problem, it offers a way to address these seemingly kind of abstract questions. And so what you might be asking is quantum-y about single molecule microscopy. So in this case, we collect the light with an objective, and the light the state of the photon that we collect from the point emitter at the objective immediately after we've collected it and sent it into our microscope looks something like this. So some amplitude function that looks like, that has like a hard circular aperture, and some phase function that actually, this is the part that contains all the information about the XYZ position of the molecule. That would be the X, Y, and Z appearing in this phase factor. And so the point is, really what we're trying to do is extract information that's encoded in the phase among spatial modes at the Fourier plane, the relative phase, the coherence, and then do something to the light in such that we optimally turn this information that's in the phase here into information that's in population differences here. And then, and then we can do photo counting on our camera and hopefully extract as much of that information as possible. And so there are generalizations of the classical Fisher information and the classical Kramer-Rao bound that give us metrics that can treat this problem. And so, as you may know, there are concepts of the quantum Fisher information and the quantum Kramer-Rao bound, where without going through the math, basically, if the classical Fisher information depends on some logarithmic derivatives of a probability distribution, you can do some hand waving, say, okay, instead of a probability distribution, I have a density operator that represents a quantum state. Instead of this derivative of a log, I have this logarithmic derivative, which is an operator defined implicitly in this equation. And so in the end, you can produce a number of the quantum Fisher information that bounds the classical Fisher information for any microscope or any measurement you choose. And likewise, the quantum Kramer-Rao bound, the inverse of this quantum Fisher information, is now a lower bound to the classical Kramer-Rao bound for any particular microscope or measurement. So in other words, when you calculate the classical Kramer-Rao bound, you have to specify what the rest of your microscope looks like. Whereas to compute the quantum Kramer-Rao bound, I'm optimizing over all possible measurements, whatever that means. As an aside, I certainly didn't, go along this path in my research in a vacuum. So this was really the paper that inspired me to start thinking about things in these terms. So this is a work from a few years ago by Man-Kai Seng and others that was mentioned by Saikat Guha, I think, a couple of weeks ago. So here he was looking at the problem of resolving 2-point emitters just in one-dimensional space using a microscope, and found that basically, if you just look at direct imaging, like standard microscope design, and bring two objects together, of course, your ability to tell the difference, to resolve these two objects gets worse and worse as they come closer together. But actually, if you view this as a quantum estimation problem, you'd realize that there's information left on the table in the form of phase, basically, that you can redesign your microscope to extract more optimally. And actually, your information as a function of the distance between these two objects does not go to zero. So this is what inspired me, but the difference here is that I'm talking about the three-dimensional position of a single emitter, and actually really focusing on the Z, the depth of that emitter, because that's kind of the more interesting parameter to think about. Okay, so to compute quantum Fisher information, as I said, I need some quantum state to plug into those equations. And what I'm talking about again is the quantum state of the photon that the single molecule emitted. And I'm starting by describing that state at the back aperture of the microscope objective, once it's really entered my microscope. And so you can think of this as some mixture of, in any particular temporal mode, this would look like some mixture of 0 and 1 photon states, where the 1 photon state is really what carries all the information and looks like a superposition of spatial modes weighed by this classical wave function. weighed by this wave function that would come up even in a classical optics description. And again, the information here is about X, Y, and Z position is all contained in the phase factor of this state. Okay, so skipping mathematical details, as a sanity check, I computed the quantum Fisher information, quantum Cramer-Rao bound, corresponding to X, Y, Z parameter estimation for any microscope, and compared them to the classical Cramer-Rao bound for X, Y, and Z of the standard microscope. That is just objective tube lens camera. And here's what I found. So to orient you, these plots on the left here are X and Y, which in this case are treated symmetrically. So there's no difference between the X and Y dimensions. And on the right is the Z of the molecule. The units on the Y-axis here are somehow, are precision in some sense. So lower number is good. If you want to turn this into like actually, all right, 10 nanometer precision, right? Or some number of nanometer precision. Basically, I'm just saying if you assume that each photo count is independent of one another, then just divide this number by square root the number of photons. Okay, the gray box in each of these panels is bounded above by the quantum Cramer-Rao bound, this number that I computed for this problem. And so, and then this solid line corresponds to the classical Cramer-Rao bound of this particular microscope design, in this case, the standard microscope. And so if this were performing optimally, you would find a range or a point at which the solid line touches the gray box, the top of the gray box. And of course, it can't go into the gray box. Right, so optimal performance corresponds to kissing the top here. And so just as I said, as a sanity check, what this is telling us is that the standard microscope, when focused, gives you the most information about X and Y you could get by, after collecting light through an objective, basically. And this is not so surprising because this is basically reflecting the fact that a microscope is designed specifically for two-dimensional imaging, and it performs optimally for that as long as you've focused your image. Okay, but that's not the case for estimating the depth of a molecule. And so I've already shown this picture of the classical Cramer-Rao bound with respect to Z of the standard PSF, but I'm kind of cutting out a lot of the details which are up here. Remember, it blows up at near focus, and it also, as you move out of focus, it worsens as well. But what I was surprised somewhat to find is that over this full range of Z, it arguably doesn't come close to the optimum, the quantum Cramer-Rao bound for Z estimation. And so no matter what level you defocus your microscope to, you're leaving a lot of information about Z on the table. Okay, so as I said, maybe that I was a bit surprised by this, but also you could argue like that's not so surprising because people know that you have to invent all sorts of fancy microscopes to do 3D imaging. And so I one by one went through any of these that I could easily program into MATLAB and found that same gap more or less exists for all of them. So here I'm just showing you 3 select microscope designs just by name without telling you what the details are that were specifically produced for 3-dimensional imaging. So these microscopes are used for 3D imaging. And I chose these because for this figure because these all have some parameter associated with them that I can tune to tune the strength of the response. Basically, like, do I want to make it more optimal over a narrow range, or less optimal but kind of evenly optimal over a wider range in Z? And I just wanted to give each of these a fair shake. And yet I still found that there's this pervasive gap in performance, that these do not perform optimally for the task of 3D imaging. And this dashed line is really just a heuristic. They all seem to conk out at more or less the same place, suggesting that there's some other bound that they're being stopped at. But I'll tell you that I don't have an equation for this yet. It's just very suggestive, and this is something that we're looking into now. I'll also take this opportunity to say that, okay, for some, if you're used to thinking about a certain kind of quantum estimation problem, you might say, well, this is only a factor of about like 1.5 off in precision, or factor of square root or square of that in information. And so this might not be a huge difference for when you want to talk quantum metrology, you want to talk about orders of magnitude improvements, right, in sensitivity. But I will say that this does matter for single molecule microscopists, because what this means is basically this would be the difference between your molecule lasting twice as long. So for instance, if it were like traversing the cytoplasm, you're trying to get some track of the molecular position as a function of time and turn that into some information about the viscoelasticity of the cytoplasm. Basically, this would be the difference between getting a track that's, I don't know, 5 seconds long and 2.5 seconds long, which is significant for these types of experiments. Why do you have a finite number of photons is basically because a single molecule will only go through so many optical cycles before it bleaches irrecoverably. And so it'll give you maybe 1 million photons, and then that's it. So you have to usually choose how to spend them, whether you want to blow them all in a short period of time or stretch them out over a longer period of time, but then of course suffer from worse precision in any particular measurement. So this matters actually to single molecule microscopists, is my point. Okay, so these existing microscope designs apparently don't saturate the quantum Kramer-Rao bound for 3D imaging. So what type of microscope would saturate that bound? And again, because I set things up in this quantum information theory framework, I had concrete mathematics to work through to answer this otherwise seemingly abstract question. And what I came upon was this microscope design here on the left, which is basically a certain type of interferometer appended to a microscope, wherein we'll walk through it here. So at this point, you would see, this is just the Fourier plane or a conjugate Fourier plane of the microscope. So basically, a point emitter would produce a disk of light, and remember, its phase. The phase function here is what contains the information about X, Y, and Z position. Okay, then I'm going to relay it to this annular mirror, at which point I'm going to make a cut in the wave function, where I send a ring of light this way and the inner disk of light this way. And I might leave myself some wiggle room as to like, what should the radius of this annular mirror be? Okay, now if we trace this arm of the interferometer through, it's a matter of doing some shrinking this disk down and then expanding it with a pair of axicon lenses. So, pyramidal or conical prisms that turn disks of light into rings of light, such that now if I just relay this other arm of the interferometer directly to a 50-50 beam splitter and record the interferogram, I would get a response that looks like this. So when the object is in focus, I have equal intensity in the two channels. When it's on one side of focus, I have more intensity in one channel than the other, and vice versa if it's on the other side of focus. And so you can see how you would turn just this ratio of photo counts into an estimation of Z. And so when I was coming up with this design, I purposely left myself some wiggle room in, as I mentioned already, in where I set the radius of this annular mirror. I also gave myself some wiggle room in where I set the magnification of this or demagnification of this telescope here. And then I did some numerical optimization over these two parameters. And just to show you a slice of the optimization here for fixed M, for fixed demagnification, but variable radius of that annular mirror, what I found is that indeed the classical Kramer-Rao bound of this microscope design over some region of parameter space performs optimally. It hits this gray box and then very satisfyingly like doesn't continue into the gray box. Why is this a flat line instead of just an extremum? It's because I'm adjusting other parameters in here that I'm kind of sweeping under the rug to compensate for this adjustment. But anyway, very satisfyingly, respects the gray box and says that this is a valuable and valid way to view microscopy, in my opinion. Just to shed a little more insight onto this microscope, a deeper look revealed that what it was really doing is performing a measurement that amounts to a projection measurement onto the eigenstates of the symmetric logarithmic derivative with respect to z. So this is an operator that, if you'll remember, goes into the computation of the quantum Fisher information and quantum Kramer-Rao bound. And this is one sufficient but not necessary condition for achieving an optimal measurement. And indeed, this microscope design here that I've gone through basically splits light into, it shunts light to camera 2 if it's in one of these states, and it would shunt light to camera 1 if it's in the other. Okay, so I did want to say something something about more recent work. So luckily, my student Cheyenne Mitchell has been hard at work doing some follow-up studies, and something interesting that she's found that we're still picking apart is the fact that, well, whether the point spread function is considered as a Gaussian or as that resulting from a circular aperture, which of course is what's actually going on in microscopy, gives or has some implication on whether you can actually achieve the optimum by just defocusing. And so the reason I started thinking along these lines is because there was a paper a couple of years ago that I probably should have cited here that was saying that all you have to do is defocus, but of course they assumed a Gaussian point spread function that might be valid for if you're trying to passively measure the displacement of a Gaussian beam, sure, but for microscopy that's not such a faithful model. And so what we found is that if you scale the Gaussian point spread function and the point spread function produced by a circular aperture, which of course in focus would produce an airy disk, such that they contain equal amounts of information about X and Y in focus. So basically I've scaled them so that their peaks coincide with one another. And of course, both coincide with the quantum Kramer-Rao bound associated, or actually now I'm confusingly flipped this around and plotted things in terms of information. So the inverse. So now big number is good. So the quantum Fisher information coincides with the classical Fisher information about X and Y at focus. And so if you scale them for this to be true, then what we're finding is that the information they contain about Z position, well, for one, the quantum Fisher information about Z in the Gaussian PSF is much larger, about 3 times larger than that contained in the actual microscopy point spread function. And so that means there's just more information on the table available if you're looking at the displacement, if you're passively looking at the displacement of a Gaussian beam rather than the displacement of a point source in a microscope. And moreover, even aside from the fact that these quantum Fisher information values are pretty different, starkly different, the classical Fisher information associated with the Gaussian PSF actually saturates the quantum bound at just a little bit of defocus. So this is saying that if you're trying to passively measure the displacement of a Gaussian beam, all you have to do to perform optimally is defocus a little bit. And this is also saying that not so for well, I already knew that from my previous work, but this is just to highlight in contrast to this Gaussian PSF case that there's less information on the table when you're talking about displacement of a point source. And also defocusing doesn't even get you to that optimum. Okay, so where am I headed with this? I think there's a lot more. Yeah, Paul has a question, I think.
Oh, yeah, the question was just with your conical measurement system, how does the lateral resolution go if you use that?
Yeah, it's worse. So this is an ideal microscope for measuring Z position specifically, not X, Y, and Z. I can prove to you that there is a measurement that would saturate all the X, Y, and Z bounds simultaneously. But I decided to focus on the simpler problem, which is just the depth information.
So proving that there is a measurement is different than knowing how to make that measurement?
Exactly. That's exactly true.
Make it then as well?
I don't. I remember seeing one claim that there was, but I honestly haven't been through the math carefully enough to don't know whether I believe it. So a lot of times you'll see in these papers, like people kind of neglect light that is, they don't always compare apples to apples. I'll just leave it. So I'm not sure, but I can prove to you quite easily that that there is a microscope arrangement that that it exists. So also, I mean, that kind of reasoning is what led me to keep going and come up with this, somewhat complicated design, because right off the bat, I knew that, okay, there is a sequence of linear optical elements that will perform an optimal measurement. So it's worth thinking about keeping going and until I find that.
Yeah, that's cool. Thank you.
Okay, and so one of the directions I'm going in next is that, in single molecule microscopy, we're often interested in parameters other than just X, Y, and Z position of a molecule. We're often interested in looking at the polarization statistics of the light as a proxy for the orientation of the molecule that emitted it, or how rotationally floppy it is, and so forth. There's lots of parameters that we're interested in measuring in single molecule microscopy. And so I think there's room here to go through these basically one by one, and also in groups, because multi-parameter estimation is always a different animal than single parameter estimation, and apply this framework and see what we get. So I think, in the best cases, I hope to find regimes where we should really build our single molecule microscope in this way, because there's a lot of information left on the table, and this could allow us to discriminate between, for instance, two binding modes of an enzyme that's been labeled with a pair of fluorophores, whereas maybe we can't do it, haven't been able to resolve these substates just by guessing at how to do the experiment. I'll also say that, actually, in the past couple of years, while I've been trying to get a job, at least one of my colleagues, Matt Liu, who I co-wrote papers with in my PhD, has really picked this up and applied it specifically to problems of measuring orientation of molecules and position and orientation simultaneously. He's found some neat things. So that's heartening that at least one other person is interested in going in this direction. And then, of course, there's the prospect of introducing some more quantum-y aspect to the measurement. So, I have only vague thoughts on this right now, but, for instance, could we excite with squeezed light and get a more stark metrological advantage? And I guess something I think about here is okay, squeezed light is useful in something like LIGO, where you can't just throw more light at more classical light at the problem, because you start to run into thermal effects that start to worsen your precision as a function of just pumping in more light. And I think we have a similar situation here. We don't always win by just turning up our laser intensity. Well, one, because the molecule will saturate, its optical transitions will saturate, so it'll only give us so many fluorescent counts per second anyway. And two, we usually don't want to operate at saturation, because the molecule, like I said, is only going to give us about 1 million photons before it bleaches irreversibly. So we really want to think about how to use how to spend the optical cycles of the molecule as wisely as possible. So maybe there's there's something to be explored here. And so I was a bit long-winded on this half, so I think I'll go a little quicker here, hopefully. But the other half of my lab is interested in using nitrogen vacancy centers to do nanoscale magnetic resonance imaging and spectroscopy. So probably, as I said, many of you are familiar with these, but these are defects of the diamond lattice wherein basically you replace one carbon with a nitrogen atom and a neighboring carbon with just a vacancy. Actually, it's an NV minus in its most useful form. So this is, there's an extra electron here. And it's an electronic spin 1 system that exhibits relatively long coherence times in its spin states, even at room temperature. So T1s of like milliseconds, T2 stars, T2s on the order of like hundreds of microseconds, usually in the best case. So that's one property that's nice. So long-lived spin states. It also has spin state dependent fluorescence. So these things fluoresce. It basically behaves like a trapped molecule in some ways. So its energy levels are nice and quantized. They sit in the band gap of diamond, and they fluoresce like a fluorescent molecule. But depending on whether they originated in the ms equals 0 spin state or the ms equals plus or minus 1 spin state, they can be they're brighter or dimmer, and so you can read out what the spin state was based on the fluorescence. And also you can polarize these on demand because because of some imbalance in transition rates. Basically, if you hit it with a laser pulse for about a microsecond at sufficient power, it will polarize into the ms equals 0 spin state, and then you can, of course, well, as I'll show you here, then you can apply microwaves and create superpositions of its spin states. Okay, so here's just a pictorial kind of showing what I just said in words. Usually when we're talking about doing quantum sensing or sensing with the NV center, we're talking about sensing in the Hilbert space spanned by just the spin sublevels, ms equals 0 plus or minus 1. And then we use the fluorescence just as a way to read out the spin state. And so, as I said, due to some imbalance in transition rates that I'm not going into the details of here, ms equals 0 state is relatively bright, and ms equals plus or minus 1 state is about 30% dimmer in terms of how many fluorescent photons it gives out. And at 0 field, due to some spin-spin interaction, this splitting between ms equals 0 and plus minus 1 is at 2.87 gigahertz. So it's in the microwave, I guess low energy microwave. And so we can record. So basically a sensing sequence or an experiment with an NV center usually consists of shining a laser light on it to read out spin states and shining microwave radiation on it to manipulate the spin states. And so the simplest experiment you can do with an NV center or a group of NV centers is record an optically detected magnetic resonance spectrum, or ODMR, wherein you just shine the laser light continuously, count fluorescent photons, turn on the microwave radiation, and sweep the frequency through the resonance. And when you hit this resonance, you'll be populating the dimmer states at a higher rate than you were before you were applying that resonant microwave. And so you see a dip in the fluorescence counts as you move through that resonance. And then the other ingredient you need for the simplest version of sensing with nitrogen vacancy centers is the fact that in response to a magnetic field, the ms equals plus or minus 1 states split. This is just a Zeeman effect. And so if you repeat this experiment, but at a non-zero magnetic field, shine a laser light, count fluorescent photons, turn on microwave radiation, and sweep the frequency, you'll now see 2 dips in your ODMR spectrum corresponding to 2 transitions. And the distance between these dips in frequency space is proportional to the magnetic field, basically. The magnetic field projected along the nitrogen vacancy axis more precisely. Okay, so magnetometry with NV centers is really just a matter, or in its simplest form, it's just a matter of looking at the splitting in this ODMR spectrum. Those were cartoons. This is actual data from an NV magnetometry sequence where actually I was looking at not just a single NV center, but a diamond containing many NV centers, an ensemble of NV centers, which are useful for certain applications. And, in these ensemble diamonds, ensemble NV diamonds, NVs are usually equally likely to occupy any of 4 orientations allowed by the diamond lattice, right? And so when you do magnetometry, ODMR magnetometry with an ensemble of NV centers, this is more faithful to what you would see. You don't see 2 lines, but rather you see 8 lines, 4 orientations times 2 transitions, ms equals 0 to +1 and ms equals 0 to -1. So that's why there's 8 main features here. And then if you look more closely, there's additional splitting here. This is due to hyperfine interactions with the nitrogen nuclear spin. But for what I'm about to tell you, you can just ignore that today. Just focus on the fact that, okay, there's actually, if you're doing ensemble NV magnetometry, there's actually 8 resonances to keep track of. Okay, and so this is not a bad thing necessarily that just complicates our lives. Actually, this gives us more information, right? And in fact, because the splitting in the ODMR spectrum is proportional to the projection of the magnetic field onto the NV axis, if we have 4 such NV axes, then we potentially have we're measuring 4 projections of the magnetic field simultaneously. And so we have an overdetermined problem that, in fact, if we want to do vector magnetometry. Okay, and so this is routinely used for vector magnetometry. But one problem that I'm going to focus now zoom way into, or one limiting factor, is that doing vector magnetometry with NV centers like this typically requires an applied field in addition to the field the stray field you're trying to measure from the sample. And that applied field has to be significantly larger than the fields you expect from the sample, such that you first separate these 8 orientations from one another so that there's no ambiguity, they don't overlap with one another, and then any shifts from the sample magnetic field are relatively small so that they don't blend into one another. And so this could be limited, for instance, if your sample is particularly sensitive to external magnetic fields, or if there are other reasons you would want to not apply an external magnetic field, let's say. And so this is one of the first problems I thought I got to work thinking about when I joined my postdoc group, because I thought I had a way to solve this problem that relied on my optics experience, basically. So I guess first, though, to put a finer point on when this could be limiting, here I have a slice of meteorite that's has some magnetic grains in it, and so zooming in here to just one chunk of this magnetic feature called a chondrule, if I take the ODMR spectrum and each of these pixels across the image marked with an X, that's what I'm showing on the right here. And so what you'll see is that, well, for one, I'm not seeing the hyperfine coupling or the hyperfine splitting anymore, but like I said, just ignore that for now. That's not so interesting, actually. But you can see that, all right, evidently at this point in the image, the applied field is much stronger than the stray field from the chondrule. And so I can clearly resolve these 8 peaks from each of the 4 NV orientations. But now as we move through the image, evidently we move through some strong magnetic feature at which the stray magnetic field starts to rival the applied field, and you lose your ability to resolve the magnetic field. Because 8 peaks turns into 4 peaks, turns into 2 peaks. And so basically, if you were just trying to do your ordinary vector magnetometry with NV centers, your field reconstructions would fail. And so, as I said, I thought I could tackle this problem using my optics background. Basically, just making note that each NV orientation has some signature distribution of photon momentum and photon polarization at the Fourier plane. So here's a calculation, a prediction based on a calculation I did very early on in my postdoc career. And then I went and measured it and confirmed more or less that these distributions are there. And then I use these signatures to come up with this modulation scheme, wherein I stick basically a very simple filter at the Fourier plane of the microscope, collect a few different measurements, and then demodulate using some, basically I multiply by a matrix that I've calibrated, I've determined previously, and then resolve, I can isolate the contributions from each individual NV orientation. So here, just to show you, in a case where you actually wouldn't need it, but just to show you that it works. Here, if I apply a strong magnetic field and take an ODNMR spectrum, I see clearly eight resonances. And if I apply my modulation scheme, then I can more or less isolate each of the individual orientations. With a little bit of crosstalk, it's about 1% error. Okay. Now, in a case where you would actually need this is if you try to do this measurement at low field, where all of these eight resonances sit on top of each other and provide nuisances to one another. Then this modulation scheme provides a way to isolate, is the only way, well, maybe not the only way, but it is a way forward to isolate the contributions from each individual NV orientation. And so because this modulation happens at the Fourier plane, it's very compatible with wide field imaging. Basically, I'm doing this modulation, demodulation to every pixel in an image simultaneously. And so I can do things like, okay, so here's a demonstration where I put a magnetic bead on an NV ensemble. First at high field, I do some vector magnetic imaging to get a ground truth, so it looks like a magnetic dipole, fine. Then I repeat the experiment, but remove the bias magnet basically, so that they're at low field, all of these resonances are on top of each other, and only when I decompose them with my optical scheme can I reproduce basically that same dipole pattern. And now returning to this slice of meteorite, again, where here are the ODMRs corresponding to each of these pixels marked with an X. If I apply my optical decomposition technique, I can resolve these blobs into their eight contributions, four individual contributions, and then reconstruct images of the magnetic field that I couldn't before. So basically, what I'm showing you here in the top panels are the X, Y, and Z components of the magnetic field corresponding to this square right here. And these were I could only get something sensible here if I did my optical decomposition technique. That is, if you don't do this and you try to just rely on this, you get nonsense. And okay, how can I verify that it's something reasonable? Well, it basically looks like a pretty simple model of a couple of dipoles on top of some background. Fine. Okay, so now just a couple more slides to look forward. So that was all an application of NV centers for DC magnetic sensing, and very much where my lab is more motivated is in using NV centers for AC magnetic field sensing, in particular to sense magnetic fields emanating from nuclear spins in a molecule or electron spins in a labeled molecule, to do basically NMR and EPR, but with the nanoscale resolution afforded by NV centers. And so just to give you some insight into how these go, basically AC sensing with an NV center is a matter of controlling the quantum state of the NV center spin and flipping it at a frequency that matches or comes near the frequency of the field. And so, okay, it's a little more quantum-y, I guess, in that aspect. And some variation on this allows us to basically get the equivalent of a free induction decay due to some nuclear spins in a nanoscale sample. And okay, where we're really headed in my lab is to do this sort of thing, but on the level of a few molecules or even down to one molecule, and applying this sort of nanoscale NMR scheme to problems in molecular biology, in soft condensed matter, and also pushing for single molecule NMR, which is a goal that has been articulated by many others than me, especially those in the NV community, but I think I have something, but it hasn't been done yet really convincingly. And I have something to contribute to this group, I think. And so let me just put one more finer point on what would make this more quantum-y as we move forward. So integral to our sensing schemes where we're really pushing the sensitivity will be protocols that look like this. So this is really the most basic protocol too that looks like this. So basically where you have some period of accruing phase and proportional to the magnetic signal on the NV electronic spin, and then swapping that state with the nuclear spin of the nitrogen that makes up the NV center. Why would you do this? Because the nuclear spin is much longer lived than the electron spin of the NV center. And so basically this serves as a long-lived memory qubit. And so you can now read out the state many times and acquire a better signal to noise by some repeated application of C0 gates and measurements of the NV center. Okay, so things like this and probably things more complicated than this will be integral to our future work. And so with that, as I said, we're kind of going in two directions here, both viewing single molecule microscopy as a quantum estimation problem, also pushing nanoscale NMR and EPR using NV centers. Here are my co-authors on the work from my postdoc that I talked mostly about today. And here are some pictures of my current lab members, including Lakshmi, who just joined us last week. So we're growing and it's an exciting time. And yeah, I'll end there.
Well, thank you for an excellent talk.
Absolutely.
We're getting a bunch of hand claps. All right. Does anyone else have some questions for Mikael? So, Yuji?
Yeah, I had a question on the super localization part.
Yep.
Previous slide. I think you mentioned that there are some schemes that can making sure that the chromo raw bond for all XYZ direction to saturate the quantum chromo raw bond. Is that true?
Yep.
But I guess for the other problem that we met before, we noticed that sometimes you have to making sure that you can the optimal measurement that you use to saturate the bond will need to know some information about the other parameter. Do you also have that kind of problem? So for example, if you would like to saturate the chromo raw bond for the Z direction to the quantum chromo raw bond for Z direction, you may need to know perfectly the information about X and Y.
X and Y. So that's not true for X, Y, and Z, but it is possibly true for other sets of parameters, like you say. Yeah.
I see.
Yeah. So, I mean, basically, you can have off-diagonal elements in the quantum Fisher information.
Mm-hmm. But in your case, it is just diagonalized?
So for X, Y, and Z, that quantum Fisher information matrix is actually diagonal.
Oh, I see. That's much different.
Mm-hmm.
Thanks.
But yeah, so, I mean, I mentioned like where I want to go with this is like, let's think about all this whole range of parameters that we're interested in measuring in single molecule experiments. And I fully expect like a lot of sets of those parameters will not lead to diagonal quantum Fisher information matrices.
Sure.
Paul?
Yeah, so the technique you're using with the apodization to pick out your certain spin states, I think is really interesting. The question is whether or not is the light actually unpolarized that's coming, or these are actually different polarization states as well. I wasn't clear on that.
Okay, so it is polarized. So the NV sensor, its optical transitions proceed mainly via two transition electric dipole moments that are perpendicular to the NV axis. So each of those dipoles, you can imagine just like, okay, I'm used to thinking about this as like, what is the far field pattern should look like that of a classical dipole radiating, right? Except for that there are two of them and I should add them non-coherently, right?
Good. Yeah, I understand. So then the question is whether or not there's an even better measurement. I mean, I like yours because it's really simple, right? It's just it just blocks off half of the thing. But whether or not a measurement that instead would use like a more generalized vector polarization spatial mode hybrid.
Yeah,
state.
I think that's absolutely possible. And I haven't, I didn't analyze this problem much more deeply than that. Part of the reason why this appealed to me also was because it was so simple. And also when I was, kind of the only optics person, or yeah, my estimation, I was the only optics person in my lab at the time, and kind of just thrown into this position. I was like, well, I don't have like a spatial light modulator anymore, or these other fancy things. So what can I do with like a knife edge and a polarizer? And so, yeah.
So do you have a way of quantifying how far you are away from some potential optimal measurement using the same sort of, quantum rail bound?
Yeah, I think in principle, something similar should work. I mean, something a little bit different here is that you're really measuring each of these individual NV classes. You're measuring on top of a background provided by the other three. So that complicates the problem a bit.
It complicates the actual, how do you get to the chroma rail bound, or just calculating what the chroma rail bound is?
How do you get to it, I guess?
Yeah.
I mean, also just, it's going to be, I mean, relative to just measuring, oops, knocking my camera around. Relative to just measuring the orientation of a single NV center where you just have one of these, say, on top of no background, it's going to be much more difficult to measure this on top of a background provided by the other NV orientations.
Right, although you somehow managed to do that before with your scheme, right?
Yeah. So it's not impossible, but it's harder. Yeah.
Yeah, I think that's really interesting. Thanks.
Well, thanks a lot for a very interesting talk. Hopefully some people have some ideas about things they want to collaborate with you on going forward. So thanks a lot, everyone.